Welcome to Everything STEAM. I'm your host, Sam Stanford. As a physicist and structural engineer with Jacobs Engineering, I've made many connections with some bright individuals who are either working, studying, or self-taught and passionate about our particular topics of discussion. For this episode, Everything STEAM teamed up with the Lowell Observatory to discuss all things Pluto. Both of my guests today hail from the observatory and are primed to highlight the history of Pluto's discovery, the science of Pluto, the Dark Skies Initiative, and how their observatory plans for the future. So if you want to learn about the determinism of Pluto's title, the features discovered during the New Horizons mission, and the observatory's inclusion in present-day astronomical projects, then you, my friend, have clicked on the right episode. Now, please let me introduce first Kevin Schindler. Kevin is the historian and public information officer at the Lowell Observatory in Flagstaff, Arizona, where he has worked for 27 years. He shares Lowell's long history of research and exploration through writing and public presentations. Kevin writes articles for a variety of publications and contributes to a bi-weekly astronomy column called View from Mars Hill for the Arizona Daily Sun newspaper. He has also written 7 books, including a book called Pluto and Lowell Observatory. And fun fact, Kevin has both a fossil crab and an asteroid named after him. My second guest featured in segment 2 is Dr. Will Grundy. Will is a planetary scientist at the Lowell Observatory who received a PhD in planetary science at the University of Arizona in 1995. Dr. Grundy does spectroscopic, thermal, and imaging observations of outer solar system bodies using numerous large ground and space-based telescopes including Hubble, Keck, Gemini, DCT, IRTF, and MMT. Targets of these observations include icy satellites and Kuiper Belt objects, as well as some of the larger bodies like Pluto, Triton, and Makemake. He also studies cryogenic ices and ice mixtures in the Astrophysical Materials Laboratory at Northern Arizona University. Additionally, Dr. Grundy is involved in projects to discover Kuiper Belt binaries, along with determining their mutual orbits and masses. Most important to the purpose of this episode, Dr. Grundy is a co-investigator on NASA's New Horizons mission. This is the mission that encountered the Pluto system in 2015 and the Kuiper Belt object Arrokoth in 2019. So, now that you've been introduced to my guest stars and the topic of this podcast, we're going to head into our first segment where we will dive into the discovery of Pluto with Kevin. Cheers. Kevin, welcome to Everything STEAM. How are you doing today?
Hey, I'm doing great. Thanks for having me on.
Absolutely. It's my pleasure. Like I was just saying to you previously, I'm really excited about this podcast. I've been talking it up for a while. There's an extreme fascination for Pluto in the sociological aspect, not only just the astronomical and what we found over time. So I'm really hyped to have you here and also to represent Lowell Observatory. So thanks.
I've been talking it up for a long time too.
Well, good to hear. Yeah, well, yeah, you definitely have. So, yeah, this first segment is going to be dedicated to the quest for Planet 9 and the story of the discovery of Pluto. So I won't waste any time. I'm going to hand it over to you, Kevin, because you're the historian. You're the man, the right man for this job. So please take it away.
Okay, I'll try to give a semi-condensed version. So if we go back and look at our solar system, historically, we knew about Mercury, Venus, Earth, Mars, Jupiter, and Saturn, because you can see them with the unaided eye. You don't need a telescope. So we don't know the first people to see them at, ancient times. But in 1781, William Herschel discovered Uranus. And that was a pretty interesting thing because it expanded the solar system. And it told us the solar system is bigger than we thought. And that was great. But then as scientists studied it, they realized that something seemed to be wrong. They kind of predicted what its orbit should be, but it wasn't orbiting like it should. It seemed to be kind of wobbling in its orbit some. And so scientists thought, there must be another planet out there whose gravity is tugging on it a little bit, causing it to pull. And so for years, scientists worked on this. And in 1846, 2 different people came up with a solution. And one of them had sent their prediction of where this would be, where this new planet should be, based on Uranus moving, wobbling like this. There must be a planet located here of this size. And they looked and discovered Neptune.
Yeah, in one night.
In one night, you could say Neptune, in a lot of ways, was discovered mathematically. I mean, they still had to look and find it, but predicting where it would be located. And so that added, 2 planets to the solar system. At some point, we could talk about what a planet is, because at one point, asteroids were called planets. At one point, the sun and moon were both called planet. Yep. So our idea of what a planet is has changed over time. And we certainly see that in modern times with, Pluto. Is it a planet or something else? So anyways, Neptune was discovered in 1846. But some scientists realized this doesn't seem to account for all those irregular motions. And so one of these scientists was Percival Lowell, who established his own observatory in Flagstaff, Arizona in 1894, 18 years before Arizona was even a state. He set up shop here. And so he set up shop actually to study Mars. And his initial, reason was to prove that there was intelligent life on Mars. And he built consciousness about life in the universe. And he was such a magnetic speaker, and he wrote newspaper columns and public books, as well as some scientific papers and such. But he built this consciousness of life out there, and it really inspired a lot of people, from scientists who wanted to either prove or disprove him, and a lot of scientists were skeptical, but it also inspired writers. Today, writers, you center a lot of stories about what is popular or what's happening in current society. There's probably a lot of books coming out that center around COVID. That's what's been controlling our lives. Well, Percival Lowell built such a consciousness about life in the universe that the likes of Edgar Rice Burroughs and H.G. Wells wrote books with this Lowellian idea of life on Mars. And so he really, he didn't inspire the creation of science fiction, but really it expanding as it did, he had a lot to do with that. Not intentionally, but it's a kind of an interesting side story.
Oh, absolutely.
So in 1902, he first expressed an idea that he thought there was a 9th planet out there. And actually his initial reasons were different than irregular motion of Uranus and Neptune. It had to do with the motions of comets and meteor showers and such, but he got away from those ideas, and we know today those ideas were not even close to being right. but he focused on these irregular motions of the planets, and began searching in 1905. And he went through a couple different sort of series of searches. Phase 1 was 1905 till 1909 or so, and then 1910 or so till 1916. And in 1915, he actually, published an estimate of where he thought this theoretical 9th planet, which he called Planet X, would be. In mathematics, X is the unknown, so Planet X is the unknown planet. And so he was searching in 2 ways. One was, like they had done for Neptune, he was mathematically calculating where it should be. And also he was doing it observationally by he and staff looking through telescopes and trying to detect this thing through telescopes. So in 1915, he published, after years of publishing an estimate of where he thought this should be. And then he died in 1916. And with him went the search for Planet X. Well, jump ahead a decade. There was, after Percival died, the observatory, there wasn't a lot going on for a while because there was litigation, his will and how that would be passed down and everything. And so the observatory was a little bit quiet for a while, but mid-1920s, that's over with. And the leadership decided, we need to re-energize the observatory, get it back on track. Let's recommence the search for Planet X. And there were other astronomers looking for a planet, not many, but there are some others, like one of the Pickering brothers at Harvard College Observatory, William Pickering. So anyways, Percival's gone, but his idea is still alive. So they decide, okay, we're going to get this search going again. First of all, let's build a telescope that's ideal for it, because Percival had tried several different telescopes, and none of them were really ideal. Some of them, the field of view is too small or magnified too much. You want a wide field view to really survey the sky.
Hmm.
And so they talked to Percival's brother, who was president of Harvard at the time,
Wow.
Lawrence Lowell, and he donated some money to build this new facility. And just as they're doing this, they're getting this together. The director of the observatory, his name is Vesto Slifer. He's trying to figure out the other half. We have a telescope, but we need somebody to do the work, because
Hmm.
there was he, his brother, who was in the state legislature in Arizona, and one other astronomer, and they were full with their own search projects. So I love this story. Vesto Slifer, wrote letters to colleagues around the country. Might you know somebody who could help us, or do you have some funding to support this? And as he's doing this, one day he gets a letter in 1928 from what turns out to be a young farmer in Kansas. His name is Clyde Tombaugh. And it turns out Clyde Tombaugh had built his own telescopes. In fact, the one he was then using was 9-inch diameter, and he built it out of equipment around the farm. The base is from a cream separator. The tube is a grain auger.
Wow.
And so he built it out of these parts, and he's using it, and he got to be pretty good at observing planets and making drawings of them. And so he decided to send these off to a professional observatory to see, what they thought of it. How's he doing?
Hmm.
And he knew Lowell Observatory because he knew the work of Percival Lowell years ago, and they were, historically an observatory that studied planets. So he sent them there. So as VM Slifer is looking around, talking to colleagues, trying to figure out, we need help, he gets this letter from a 23-year-old farmer. And the drawings he sent are pretty darn good.
Hmm.
And he sends them a letter back and asks questions like, what kind of physical condition are you in? Are you used to staying up long nights? And from this led to Slifer saying, why don't you come to Lowell Observatory? We'll hire you on a trial basis to help us with this program, and it's to search for the ninth planet. Within a year, Clyde Tombaugh discovered Pluto, 24 years old, self-taught astronomer.
Yep.
And he discovered Pluto, and it was, his skill and attention to detail was critical to the discovery. And so you look at Percival's original search and the inspiration that later generations got to continue that search, and getting the right instrument, and then hiring the right person. It was kind of a nice confluence of events. And he discovered the planet. We can talk about is Pluto a planet or not debate later, but this was the ninth planet, and the only one discovered in the United States. And this comes at a time in 1930 when we're in the Depression. There's not a lot of good news. This is something good. This is something positive. Young guy, self-taught, American farmer. I mean, it's a classic. I wouldn't say get rags to riches story, because he didn't get rich from it, but that idea where he self-taught and he made it happen. He discovered a planet. It's just a great story. The pursuit of excellence, the teaching yourself, following your passion, and then and the name. They didn't have a name for it yet. If you discover a planet, you get to name it, and so they got suggestions around the world, but the one they liked the most. The first person, we still have several hundred letters and telegrams in our archives at the observatory, suggesting names, because when news got out, this was pretty big news. People around the world sent in suggestions of what to call it. And the one that really stuck out was first suggested by an 11-year-old girl from England, Venetia Burney. And she said, why don't you call it Pluto? Because in mythology, Pluto is the god of the underworld, and this planet is really far away. And also mythology, Pluto has siblings, Jupiter and Neptune, I think. Anyways, a couple that are already in the solar system.
Yeah.
So that kind of made sense. But there was another added nugget of coolness in that, all the planets have an abbreviation. And it's not really a scientific thing, but just kind of used in pop culture and such. So Mars is a circle with the arrow pointing up, like the symbol for males. and Venus is the circle with a cross pointing down, like the symbol for females. Well, the leadership of Lowell said, if we call it Pluto, we can use for its symbol its first two letters, a combination of its first two letters, which are P and L, which are also Percival Lowell's initials.
Nice.
A great tribute to the guy who started this search. And so that's how Pluto got its name.
That's wonderful. Wow.
And it's just a great story.
It is a fascinating story, and there's more into that I just heard that I really never even thought about. First of all, just the American aspect of it, really. I mean, especially in a time of like what you said during the Great Depression, where there wasn't much good news going around. I mean, it's a good sociological aspect to it. I'm kind of curious. Could you share any of the names that stood out to you, like as an individual, or maybe something that the observatory was considering other than Pluto?
One that they were considering, in fact, there's some evidence that they considered this more than others, was, oh my gosh, I just drew a blank.
Oh, no.
She's the goddess of knowledge, Minerva. And they probably would have used that, except it had already been used to name an asteroid, which is close enough. They're called minor planets also, close enough that they didn't want to use that name. So Minerva, it's more poetic the way it turned out because of the initials and Percival Lowell and everything. But Minerva was another popular suggestion. Cronus was one, another mythological character. There are a lot of ones that were cute. Like one person suggested name it after his daughter, and he said, she's the world to me, so I think her name would be appropriate on a planet. There was one person that suggested the word is something like Zimmel or Zixel or something like that. It was, at least at that point, like the last word you'd find in the dictionary. And he said, for the last word on planets, let's use the last word in the dictionary.
Interesting. I'm glad we didn't go with that.
Yes. I think something I find fascinating by going through all these is that if you didn't know when the discovery was made, you could narrow it down, because a lot of the suggestions grew out of the times. One of the most common suggestions was peace, or the Greek god of peace, because the 1930s were recognized as the decade of peace. In hindsight, it started out well, but it didn't end so great with World War II.
Fair.
Another suggestion of a couple different people had Lindbergh. And Lindbergh had just flown across the Atlantic in 1927. And so he was an American hero. And so, 5 years earlier, you would never have that name. 10 years later, probably not, it's not as, hot. Yeah. So it's interesting to see how you can kind of narrow down the time based on some of the names that were suggested.
Yeah. It's probably good that we stuck mythological, honestly, because that can stick around.
Yeah. And that was the tradition. I mean, even though the restrictions, it's more stringent today going through an approval process. Back then, it was still, all the planets except for our own planet are named after, gods and goddesses. So we're going to stick with that.
Can you take me through how Clyde ended up finding Pluto through the imagery? Do you mind?
Right. The idea was, Percival Lowell thought it was a really big planet, like a Jupiter size, a lot bigger. You can fit 1,000 Earths inside of Jupiter. So that's the kind of size we're talking. And that's part of the irony of the story, is that Pluto is not planet X. He was looking for a really big planet, and they found a really small one. They were, based on his predictions, they looked in this spot and they found a planet pretty darn close to where he thought it should be, but it was just serendipity. The planet Pluto couldn't account for those irregular motions of Uranus and Neptune. It doesn't have that kind of mass. And so we know today that the planet X that Percival Lowell was looking for doesn't exist, because he was doing it based on these irregular motions of Uranus and Neptune. But the best estimates of the mass of those planets, as we know now, wasn't that good. And so what appeared to be irregular motions, it was just, we didn't understand the actual mass, and so that threw us off on calculations. If we knew back then what we know today, Percival wouldn't have been looking for planet X. They
Okay.
just happen to find Pluto right there. Now, there are other scientists looking for a planet X
Yeah.
in our solar system today, but it's not like based
It's not
on
the
what
same.
Lowell's looking at. And so
Right.
it's and so they were looking for this big planet, but also realized, if you could just find it looking through a telescope eyepiece, it would have been found by now. And so we're going to search for this by doing it photographically. And so what you're going to do is take a picture of the sky through the telescope. And the telescope they ultimately used was a 13-inch diameter telescope. And it took a picture of the sky on 14 by 17-inch glass plates. They were like a big piece of film that had emulsion on one side. So each one of those glass plates, each one of those represented an area of the sky. If you hold your fist out at arm's length, that's about 15 degrees, the way we measure the sky. So that's about how much of the sky each plate was represented. So you take a picture of the sky, wait a few days, and take a picture of the exact same place. And then put them on a machine called a blink comparator. And a blink comparator is like a big microscope. And you put a plate on each side. And then you look in the middle as a microscope eyepiece that's magnifying a section of one of the plates. And when you turn this thing on, there's a mirror inside the mechanism that flips. So it flips your field of view as you're looking through from this plate to the other one, back and forth. And so you're looking at the same field of view in each one. And what you have to do is look at every single dot to see if it's changed position relative to all the others. Because most of the dots, and I'm talking about one plate that represents an area of the sky like your fist at arm's length, contain 200,000 or 300,000 dots.
Absolutely.
Most of those are stars. And so stars, compared to the planets, are much farther away.
Right.
So if we think of driving down the road and the trees on the horizon seem to be going a lot slower than the ditch right next to us, which is flying by. So the same thing in the sky, the planets that are a lot closer to us are going to appear to fly by compared to those background stars. And so, so that's why you take pictures a few days apart. In a few days' time, the stars are going to be in virtually the same place. They're all moving, but they're so far away you don't really notice it. And so you're looking for any dot to change position. If they did, then it's probably something a lot closer to us. Maybe it's an asteroid. Maybe, hopefully, it's a planet. And that's how he did it. And I don't know, that doesn't sound very easy to me, but it was a lot more difficult than it sounds.
Oh, yeah.
You're looking at every single dot to see if it changed position. The focus you have to have, the attention to detail. He was the right person for the job. I think a lot of us would, you get distracted after a while. I've looked through this. You see all these dots, they just start moving, and you got to focus. And so it was a very tedious work. In today's world, we have computers to do all that. You can write programs, and it'll detect these things, and so it's done a lot differently. But even so, when he found a dot that changed position, it could be an asteroid, which is closer, and he could measure it, and based on how much it changed position, the more it changed position, the closer it is to us.
Right.
So based on that, he could tell how the distance, and knew, okay, that's an asteroid, not a planet.
Right.
He also developed a technique where they would cancel out a lot of the asteroids, so you wouldn't get confused with that. But you could also have a piece of lint on the plate, or maybe a variable star that's bright one day, but not so much the next day.
That's fair.
So it wasn't an easy proposition.
No. So were they just pointing the telescope at 15 degrees where they mathematically thought that planet X would be, and then it just so happens that they found Pluto there?
Yep. In fact, when he started searching in the fall of 1929, he actually photographed Pluto, but didn't realize it, because Pluto was by that point getting ready to set, and so it was low in the sky. It was really not a very good image, and again, it's just a dot. And so it wasn't until that area of the sky next spring he rephotographed it. But I mean, it wasn't the first section he photographed. He systematically photographed the sky of what is what area of the sky is up right now, that's what he photographed. But the preferred place was near the star Delta Geminorum in Gemini. That was an initial focus, but in the late fall and winter, or whenever it was, it was out of the sky, so we had to wait till the next season.
Oh, that's awesome. Also, I want to just throw a good word into what was used to understand, to perceive, I guess, the motion. It's called angle of incidence. Whenever you're looking at a star that's light years and light years away, the angle of incidence is going to be way less than a degree, like 0.000, whereas like in like a 15-degree field of view, you might have something that changes at like a degree or two within that field of view. And that's where you can say, oh, relative to me on Earth, it is moving this far. So I can realize how far away that actually is, how fast it's moving, and
exactly,
how big it is.
Yeah, there's a lot of, really, it's really basic math, and yet it's, it's still complicated. And the work is certainly mind-numbing.
Yeah, it's not completely basic, but basic to the natural physicist.
Yeah, right. Yeah. Yep.
Yeah. So we're gonna conclude segment 1, but whenever we come back, we're gonna talk more about the science of Pluto and also the determination of Pluto. So stick around. Welcome back. This is segment 2, and I have Dr. Will Grundy with me. Already mentioned you in the introduction, but again, just super excited to have you on the podcast. It's such an honor. Somebody that has so many accolades. So thanks, Will, for joining me.
It's great to be with you, Sam.
So, of course, you're an expert on Pluto, being that you were involved in the New Horizons project, and we brought you on to talk about Pluto science. And then, of course, we'll get into the weeds at the end about Pluto's determinism, why it went from a primary to a dwarf planet, but then why there are still arguments and such divide in the scientific community about that determination. So, without further ado, we're going to jump into the slideshow that I so graciously put together. Hopefully, Will doesn't tear it apart too much. But what we're going to do is we're going to go through the slides one by one, and Will's going to give his 2 cents on the matter and tell us his expertise. So with that being said, we're going to jump into the first slide where it's just highlighting Pluto's size. So, Will, what do you have for me?
Yeah, so Pluto is small. It's not a very big planet. It's basically about 1,500 miles across. So that's kind of the size of the western U.S. West of the Mississippi. So if you put it up next to the globe of Pluto, next to a globe of the Earth, it's pretty small. But that doesn't mean it's not large enough to hold on to an atmosphere, which we'll talk about in a little bit, and have all kinds of interesting seasonal patterns and so on, and pull itself into a spherical shape. And Pluto's largest moon, Charon, is half the size of Pluto again, but they're relatively close together. So if you were standing on the surface of Pluto and looking up at Charon in the sky, it would be about 8 times the size of our full moon in our sky, because, even though it's smaller, it's a lot closer. Our moon is about 250,000 miles away, whereas Charon is only like 12,000 miles away.
Right. I think, how many Earth diameters is that? Man, I used to know this.
So the Earth is about 4 times the size of the moon. So when you're standing on the moon looking at the Earth, it's about 4 times larger. But if you're standing on Pluto looking at Charon, 8 times larger. If you're standing on Charon looking at Pluto, 16 times larger. So it would really dominate the sky.
That's a wonderful perspective. That be really interesting to be there to actually see that. So let's jump over, and I guess maybe I should also say that isn't it the largest dwarf planet that we've found in the Kuiper Belt so far, or am I mistaken by saying that? At least so far.
Well, okay, so it's the largest in diameter, but only by a whisker. Eris is almost as big as it is. And Eris is actually more massive than Pluto is, so it's got more rocks relative to ice in its interior. Gotcha. So, if you like mass, Eris is your your king of the Kuiper belt. If you like diameter, Pluto's your king of the Kuiper belt. They're both probably very fascinating places, but of course we've seen Pluto up close now, and it may be some time before we get to see Eris up close.
Yeah, that's absolutely beautiful. So let's move on and talk about Pluto's atmosphere and temperature, both very interesting. So I'm going to let you go after it and start with the surface temperature.
Yeah, so the surface temperature on Pluto is obviously much, much colder than it is here on Earth because it's much, much further away, almost 40 times as far away from the sun on average as the Earth is from the sun.
Right.
And the intensity of the sunlight falls off as the square of the distance. So if you square that 40, you're talking about a factor of 1,000 less intensity of the sun.
Wow.
So the surface temperature, I mean, to be honest, all of us scientists use Kelvin, the absolute temperature scale, starting at 0, where stuff is so cold that there's no motion whatsoever. And Pluto's about 40 Kelvin, where the Earth is maybe about 300 Kelvin. And
right.
Comfortable room temperature is something like that. That 40 Kelvin, though, there's quite a bit of variability because, as you can see when you look at the pictures of Pluto, there's very dark areas. Those are going to obviously absorb more sunlight and get warmer. There's fairly bright areas that reflect almost all the sunlight that hits them, and they stay fairly cold. But Pluto's atmosphere is nitrogen, and anywhere that gets cold enough, the atmosphere will freeze onto it, and that actually delivers heat by freezing onto it. It's called latent heat. So there's a lower limit where you can't get any colder than some temperature at which the atmosphere starts to condense. Of course, once you've condensed all the atmosphere, that doesn't work anymore, but it looks like that doesn't actually happen on Pluto. The atmosphere is amazingly complicated, and the interaction with the surface is amazingly complicated too. So on Earth, a lot of what makes Earth interesting as a planet from a geological point of view is the fact that water can evaporate into the air and then fall back out as precipitation or snow or rain or whatever. So basically sunlight provides power, lifts this water into the air by evaporating it from the oceans, puts it on top of mountains or other locations, and then it runs back downhill and carves things like the Grand Canyon and makes glaciers and erodes coastlines and all of that. And that's all really sunlight performing work on the planet. And the same thing happens on Pluto, but it's way more complicated because there's 3 different materials that can all go into the gaseous phase and settle back to the surface in various different locations. So it's methane, which is natural gas that you burn in the stove, nitrogen, which is the main ingredient of our atmosphere, as well as the main ingredient of Pluto's atmosphere, and then carbon monoxide, which of course is poison gas. And if your stove doesn't burn properly, you might be making that, but hopefully you've got a detector in your house that beeps if it goes off so you don't get killed. But those 3 ingredients, they're all existing both in Pluto's atmosphere and as ices on its surface. And so, imagine that you could have 3 different kinds of rain or snow on Earth. It's like, oh, it's this kind of snow today. Well, okay, guess I don't have to shovel because that one goes away fast.
Wow, that's really cool. So I wonder if if that concentration of precipitation is variant depending upon where you're at on Pluto based on altitude, I'm assuming, because I thought that methane was more of a high altitude substance on Pluto.
Yeah. So when we see these deposits of methane, they do tend to be on the ridges of, crater rims and on mountains and so on. And it's true, but the why that happens is actually pretty complicated. So methane is lighter than the other 2 molecules. And so it tends to be buoyant and stay up high in the atmosphere. But whenever there's a mountain that's poking up into that methane-rich layer and it gets cold, then the methane can freeze onto it.
Right. Sublimation, I would assume. Is that
sublimation affects all of them. I mean, at different temperatures. And so nitrogen is the easiest to sublimate. It's the most volatile of the 3.
Yeah.
And methane is the least volatile of the 3. So it's the hardest one to get rid of. But they're all capable of sublimating,
at their own temperatures.
When the season is right.
Yeah.
So it's all, it's not just altitude, it's seasonal and latitude, and the thermal behavior of the ground matters. How fast does the ground heat up and cool off, and this kind of stuff as well.
Yeah, no, that makes a bunch of sense. So with the size of Pluto, I'm trying to remember the perspective of this. I can't remember how, because obviously you get a large lack of gravity because it's so small. I can't remember how far you can jump like as a normal person. I thought it was like within like, wasn't it like 15 feet or something like that? It's quite large.
I've never actually tried to work that out. Yeah, it's like a tenth of the gravity.
Yeah, that would make sense. So a tenth of the gravity. So maybe if you could jump 2 feet on Earth, you're probably jumping about 20 feet on Pluto. Cool.
Yeah, I don't know how heavy your spacesuit has to be to keep you from freezing your butt off, but
good point. We love weird theoretics. So moving on, let's talk about Pluto's surface. So we've already alluded to this a little bit. We've talked about nitrogen, we've talked about methane and carbon monoxide. So the surface is mostly nitrogen, right?
well, okay, so this Sputnik Planitia, that glacier is mostly nitrogen, but
Okay.
actually a lot of the rest of the surface, like those dark areas, are completely nitrogen free. So you've got your little Pluto picture there on South America. You can see it's like kind of the size of, the Amazon before they started, cutting down trees.
Yeah.
And the northern polar region that sort of has a slight yellowish tinge there, that's more methane rich. So it depends where you look.
Is that maybe because is it also has to deal with altitude plus it's also
and
the inclination?
So yeah, because that northern pole is coming into summer right now, and so it's in continuous sunlight, and so the nitrogen that was there is probably already sublimated away for the most part, and it's left the less volatile materials.
Ah, that makes sense.
But your thing also with the ammonia, so there's the surface, and that's where you see a lot of these volatile materials because they're mobile, so they end up on top. But the interior is rocks and ice, like you say, and it's roughly 50-50, both rocks and ice. And probably there's also some of that, well, I shouldn't call it ice because some of it is water that probably is still liquid, and it's slowly freezing as Pluto's radioactive decay slowly tapers off. And one interesting property of water is that as it freezes, it actually expands. So you could imagine this interior ocean that's slowly freezing, that's squeezing it. And that's building up pressure. And that's one possible explanation for these kind of eruptive processes. That's, I think, maybe your next slide. Oh, no,
Getting there.
Okay, well, we'll get there when the time comes.
Yeah, so the next thing I guess we want to highlight here is that Pluto has nitrogen glaciers, which makes a lot of sense, I think, based on this pressure process you were talking about.
Yeah. So nitrogen is, so all of these volatile materials, the reason they're volatile is because the molecules don't stick together very aggressively. Okay, so it's easy to shake them apart by putting in a little bit of sunlight or energy. Okay, so you can imagine a solid made out of molecules that are not very sturdily attached to each other. They slide past each other without too much difficulty. So it's really not very hard for nitrogen ice to flow as a solid. So if due to the seasonal cycling, you're depositing nitrogen somewhere uphill, eventually there will be enough of it and it's going to flow back downhill, and it ends up in this Sputnik Planitia giant basin that's kind of lower than everything else.
That's a beautiful process.
Yeah, it's very cool, but it's also, our intuition for glaciers is based on Earth. So we have water ice glaciers, and rock is the substrate, and rock is much denser than water ice, and yet still rock gets torn up and carried along in the glaciers, even though it's a lot denser than the water ice. But nitrogen ice is actually a little denser than water ice, and water ice is the bedrock on Pluto. So imagine a glacier that's denser than the surface it's flowing over. If it finds a crack, it might just tunnel into the ground. And your slide there shows a bunch of flow lines sort of converging on this point. It's like, where's the nitrogen go after it gets there? Is that the drain?
I see that. Yeah. Oh, that's really cool.
Planum and Planitia. So we called it a planum because we thought it was a high altitude thing at first, but it turns out it's low. And so Planitia is probably the better word for it. But this was a slide from, the day after the encounter or 2 days after the encounter. So we were still figuring things out.
So we were talking about this a little bit before we jumped into the recording. So this could be possibly from an impact, right? And that created a gravitational anomaly with Pluto and Charon.
Yeah, so it's a little weird because the gravitational anomaly, to be where it is, along the tidal axis. So if you were to draw the line from Charon to Pluto, they're tidally locked to each other, so they always keep the same face towards each other. And heavy things will end up along that line, and light things will end up elsewhere, just because that's the most energetically stable place to be. But how do you make a hole in the ground be heavy, right? So there's a bit of a problem with that. A lot of times what happens is if you have an impact into a crust, the mantle lifts up underneath. And if the mantle is denser material, then even though it's a hole in the ground, the net density might actually be higher. So that's...
Oh, yeah.
And of course, that's easiest to happen if there's an ocean in the interior, which has already been hypothesized for other reasons. So it actually really holds together that there would be an ocean, or at least that there was an ocean when that basin formed, for it to have migrated towards the polar axis like that.
That makes sense. Converging hypotheses towards a subsurface ocean. That's really cool.
Right. And again, this is the density contrast between ice and water, where water is actually denser than ice. Actually, that's another thing that's funny about Pluto's glaciers. If you melt nitrogen, the liquid is lighter than the solid. So if you melt water in a terrestrial glacier, the water goes down at the bottom and it helps lubricate the glacier. But if you melt at the base of a Pluto glacier, the liquid is going to be less dense and it's going to want to come out. So it will percolate up to the surface, and I don't know if there would be geysers or if it wouldn't quite make it to the surface and it would refreeze, or who knows, but it's very different than terrestrial glaciers. And it's just, when you look at the pictures, it's like, yeah, it looks like a glacier, but you have to think about how the material properties create different situations.
Right. Liquid nitrogen lava. That would be so cool to see. Oh man, that would be awesome. Let's move on here to, we did allude to this, the cryovolcanism, but also tholins. Could you take us through what tholins are?
Yeah, so tholins are basically, how when you scorch meat in a frying pan or on the grill, it turns brown.
Yeah.
And basically, tholins is the same sort of thing happening to simple organic molecules. So methane is the simplest organic molecule you can probably imagine, 1 carbon and 4 hydrogens.
Yep.
But if you irradiate that, so you're breaking the bonds and it's recombining into messier, complicated jumble of molecular mess, those tend to have reddish orangey kind of colors. And tholins is a name that was applied actually by Carl Sagan when he made them trying to simulate the atmosphere of Titan. And it's actually just Greek for mud or murky or something like that. But these kinds of colorful, very complicated organic molecules just occur seemingly throughout the universe, because organic molecules are ubiquitous and radiation is ubiquitous. So these things just keep cropping up. It's the same stuff that forms haze it used to be much more so, but in, like the LA basin. When I was a kid, you'd fly into LA and you'd just submerge through this layer of orange muck and you couldn't see the mountains at all. It's much, much cleaner today. So, everybody's lungs are thankful for the Clean Air Act. But
absolutely. That's really cool. So yeah, and like we've already alluded to, we talked about that it has cryovolcanic activity, so liquid eruptions that come out and freeze.
Now we haven't seen these erupting. We've just seen the edifices they've built. So we're conjecturing how the process works. But one distinct possibility is as the interior ocean is freezing, it's creating pressure and it's squirting some of the liquid out. That's definitely a plausible scenario for something like this.
Yeah, and I think based on some of the imagery that I've seen, and even like the one that I have here on the slideshow, is that it's showing like obvious flow patterns from certain like geyser-esque or mountainous regions, just like what you're seeing here.
Yeah, and if you look at those close-ups there, you really don't see any impact craters on no obvious ones anyway. And that also tells you that this eruption must have resurfaced it relatively recently. This is not something that happened at the beginning of the solar system. This is something that's, either ongoing or was ongoing until, yesterday.
That's a good
geologically speaking.
right, and that's a good point. I don't think we've touched upon yet is that both Pluto and Charon don't have a lot of impact craters
Well,
compared to.
Charon does. I don't know. Do you have a good picture of Charon? Yeah, so it does have its share of impact craters, although there's an interesting deficit of the really small ones. Probably tells us more about what's going on in the Kuiper belt in terms of small Kuiper belt objects than it tells us about any processes active on Charon, but still interesting.
Definitely. So let's talk about Pluto's orbit, being that it's both inclined and eccentric. Do you have anything to add?
Yeah, so I mean, all of the planets' orbits are inclined and eccentric.
Yeah.
Pluto's is the most of the sort of the 9 classical planets, but there are Kuiper belt objects that have even more inclined and even more eccentric orbits. Actually, Mercury's eccentricity is not that different from Pluto's. It's like 0.2, and Pluto's is like 0.245 or something.
Oh, wow.
The eccentricity basically just tells you how far you deviate from the average, right? So Pluto's eccentricity is about 0.25, and so that means it comes a quarter of the way closer in and a quarter of the way further out from its average. And that quarter of a way closer in actually gets it just to Neptune, actually just slightly inside of Neptune's orbit.
Gotcha.
And if it were just doing that, it would probably eventually get into a tangle with Neptune and get kicked out of the solar system or collide or something. But it happens to be in what's called a mean motion resonance, which means that Neptune goes around 3 times for every 2 times that Pluto comes around. And every time they meet, where Pluto's in up close, Neptune's away over on the other side of the solar system. So they never get that close to each other, just because they happen to be stuck in this resonance. And resonances are common in orbital systems. You know, the moons of Jupiter are in a 3-way resonance, and there's resonances all over the place in satellite systems around other planets.
That makes sense, because if you're resonating and you're close rather than what you're saying is having 3 versus 2 like on orbit patterns, more than likely the largest celestial object is going to win, or there's some sort of perturbation where one's definitely winning, but it's still being heavily affected.
Yeah. I mean, Neptune is just so much more massive than anything in the Kuiper belt that actually a lot of the Kuiper belt objects are trapped in various different resonances with Neptune, not just the 3-to-2 resonance like Pluto's in, but there's a whole host of resonances. You basically take any 2 of your favorite integers, and there's probably a resonance with some Kuiper belt objects in it with those 2 integers.
That's fair. There's a lot of objects out there. I guess we're getting towards the end of the slideshow here. We want to talk a little bit more about Charon and the Barycenter. So do you want to take us through what a Barycenter is first? Yeah,
so it's just the center of mass of the system, right? So if you have 2 things orbiting, they're really orbiting the Barycenter. So if you had 2 equal mass things, they'd each be going around the Barycenter, and they'd each be equal distance from the Barycenter. In the case of the Earth and the Moon, the Barycenter is inside of the Earth. And that's true of all of the giant planets and their satellite systems, because their satellites are small compared to the planets. But Pluto and Charon are not that different in size. Pluto's basically twice the diameter of Charon, and so it's cubed, right? 8 times the volume, something like that. So the Barycenter is a point in space between them, and it's that green point on your plot. It's maybe something like 500 miles above Pluto's surface.
Okay.
So in effect, both of them orbit that Barycenter, and so Pluto has a leading and a trailing hemisphere, which is a little weird. It's not moving fast enough that it really makes a difference. Some of the satellites going around Jupiter are going around so fast that their leading hemispheres get much worse impact damage than the trailing hemispheres, just like the bugs hitting the front windshield and not really hitting the back windshield.
Gotcha.
But Pluto's going around, I don't know, something like tens of meters per second around that Barycenter. So it's not fast enough to really be sweeping up any bugs.
Right. Oh, that's cool. So yeah, and then the last thing is that Charon and Pluto are tidally locked. So just for the layperson, do you want to explain being tidally locked? And that's something that occurs a lot in space.
It does indeed. And so in the Earth-Moon system, we're partly tidally locked, where the Moon is locked, so it's always the same face of the Moon towards the Earth, but the Earth is still spinning. It's slowing down, so eventually it may become locked. But in the Pluto-Charon system, both of them have spun down, and so they both keep the same face towards each other. And if you're on the face, say, of Pluto that happens to be oriented away from Charon, you will never see it. And you'd have to walk around to the other side, and then it'll always be in the same place in the sky. It'll maybe oscillate around a little bit, but you could navigate by it because it's just always sitting there.
So if you figure out your spacesuit situation,
right,
you can.
And you're prepared for a long walk because it's the size of the Western U.S.
Right. Yeah, you can make it.
Did it. You could do it.
Very true. Okay, so the last portion of this we want to talk. Unless you have anything else you wanted to add based on the science that maybe we didn't cover in this slideshow. Do you have anything extra that you would like to share?
Well, there's one cool thing about Charon, which is that reddish pole. That reddish pole is, as best we can tell, the result of Pluto's atmospheric escape. And every planet loses its atmosphere at some rate. And Pluto's rate of atmospheric loss is actually about the same as Earth's, something like a kilogram per second or so. It's got enough, don't worry. But that atmosphere streams out into space, and there's Charon not that far away, and it has a strong gravitational field, not as strong as Pluto's, but strong enough that some of that gas gets attracted to Charon, hits it, bounces around for a while, and then eventually escapes to space again. But if while it's bouncing around, it finds its way to the winter pole, it's so cold on the winter pole, maybe 15 or 20 Kelvin or something, that it just sticks. And while it's stuck there, it's exposed to the radiation from space, and that drives this process of making, these heavier molecules, like I was talking about earlier, eventually go on to become tholins. Basically, all that has to happen during the winter is that they get heavy enough to stay there when the sun comes back up in the spring. When the sun comes back up in the spring, the methane all goes away, but whatever bigger molecules got formed stay there, and they keep getting processed due to continued radiation until they turn red. So it's like, Pluto graffitiing on its moon.
That's wonderful. So is that just like the gas molecules escaping the clutches of gravitational influence, or does that also have to do with a sputtering effect as well?
So the escape from Pluto is just that at the top of the atmosphere, there's always some distribution of speeds, and a handful of them are going fast enough to escape, and they escape. And some of them also get a kick from a charged particle from the solar wind or an energetic photon or something. So there's a handful that's constantly escaping. And the same thing happens at Earth and at Mercury and every planet. In fact, if you look at Mercury in sodium, you see it has a tail like a comet because it has sodium on its surface, and that gets sputtered off into space and lost to space. And so every planet is losing gas at some rate, and it's not much. It's got enough to last for the life of the solar system, but it's just an interesting phenomenon.
Yes.
And Charon is close enough and has enough gravity that it catches some of it.
Is it good enough to call moon graffiti? That should be.
Yeah, I mean, graffiti sort of implies, a little bit of law breaking, I suppose. I don't know if that counts.
That's fair. We're still obeying the laws of physics, so maybe, man, that would be fun. I mean, of course, science has the best nicknames for things.
Yeah, but it's kind of a fun example of where anytime you explore some new place for the first time, you'll see something that's a head scratcher, and you'll be like, why is it red up there? It's cool, but why is it like that? And you just have to think about the physics and the chemistry and, come up with a hypothesis. And if nobody comes up with a better hypothesis, eventually, it gets accepted.
Again, another reason why you need to have diversity looking at a problem. People coming from all different angles. So just like, wow, that's what's going on. They can understand the physics or the chemistry about certain things, geology, etc. So the last portion is talking about the determination of Pluto moving from a primary planet to what it was supposed to be, and then moving it. Was it 2015 that they said this, or was it
the IE? Are you talking about the IE thing?
Yeah,
that was 2006.
2006.
So it was actually the year that New Horizons launched.
Yeah, that's right. Right. Because you didn't get data until
2015.
2015. That's right.
Yeah, it's a long time of, are we there yet?
Yeah, I bet. What, 9 years, right?
Yeah, 9.5.
Nice.
So from the point of view of a planetary scientist, as I am, I would say that the IAU basically made a embarrassing mistake.
Okay.
Really, it was a bureaucratic problem. So they're in charge of naming things, and lots of Kuiper Belt objects were being discovered and given names and so on. But then here's, Eris, which is comparable in size to Pluto. It's like they have a mechanism, they have a process for naming small bodies, but they don't have a process for naming planets. So it's like, well, holy crap, what are we supposed to do? So we either have to figure out our process, or we just figure out a way to not have to name these things as planets, because then we can use our existing process. So really, it masqueraded as science, but it wasn't really a scientific move at all. It was they didn't even obey their own bylaws. Proposals are supposed to be published, 6 months in advance, so people can think about them and debate about them, and then vote openly. And they did it all very secretively, and they were worried about public backlash if the public knew that they were working on this. And it folds into what is the purpose of taxonomy? Why are you actually putting things into categories? And planetary scientists you'll always hear planetary scientists apply adjectives to planets. I mean, planet is a very general term. I mean, it's almost as generic as world. It's a big round thing that's not a star. But you'll always hear planetary scientists putting adjectives on that. So we're talking about rocky planets. And there's 5 of those: Mercury, Venus, Earth, Moon, and Mars. Mm-hmm. And there's gas giants. And sometimes people will group Uranus and Neptune with the gas giants. And sometimes people will separate them off and call them ice giants, because they really, Jupiter and Saturn are primarily hydrogen and helium, and Uranus and Neptune are primarily heavier elements. People will talk about icy dwarfs. People will talk about primary planets and secondary planets. So like the moon would be a secondary planet because it goes around a primary planet, the Earth, which goes around the sun. But something like Pluto and Charon would be a binary planet in a sense, because they both go around their common barycenter. And you could imagine 2 equal Earths going around their common barycenter. I mean, neither one's really a satellite, and you can't call one a primary and the secondary if they're the same.
Right.
But does that make them not planets anymore? No, of course, they're still planets. They're just qualified in these different adjectival ways. Community, that's the way the scientific community uses it. And the IAU thing is really just a big distraction. Really, nobody in the planetary science community pays much attention to it, to be honest. The public shouldn't either. So some of where this came from, a funny thing happened on the way to the space age, where around the turn of the 20th century, so 1900, all of this new physics started being discovered. Einstein's special relativity and Bohr model of the hydrogen atom, and very soon quantum mechanics and all of this stuff. So it was super exciting because you could finally understand how stars worked, and very soon the discovery of the expansion of the universe, and the fact that galaxies were these separate, vast swarms of stars in a universe that suddenly was much, much larger than anyone had ever conceived. And people lost interest in planetary science. There was not much happening in planetary science from the early part of the 20th century to the space age. Oh. And during that time, there was still this folk etymology or I should say taxonomy of planets, which basically came from astrology. It was like planets should be this small number of culturally significant things that, that have influence, right? And so when the space age came along and we were sending missions to Mars and Venus and soon the outer solar system, everyone got interested in planetary science again, but people adopted this folk taxonomy that basically came from astrology. And that's what got adopted by the IAU. It's like, okay, they have to be influential, and there can't be very many of them. That's essentially the IAU definition. And it's going to go down in history as a terrible embarrassment for that organization. But they haven't owned up to it yet, but they'll get there.
Understood. Okay. So it's more, we really shouldn't worry about like these, the sociological ordering of planets. It should be more like, these are behaving like binary planets. This should be a binary planet. Or this should be an icy giant, or this should be a gaseous giant, I mean,
the more we have, the better, because you can compare and contrast, and each of them presents interesting uniquenesses of its own. It's like, if you don't care about dinosaurs, you don't need to learn a whole lot of dinosaurs. You don't need to learn any dinosaurs. But kids that care about dinosaurs, boy, they can wow you. They can memorize hundreds of dinosaurs. And we probably ultimately, if you count the moons, the large spherical moons, we probably have well over 100 planets in our solar system.
Yeah.
And as a planetary scientist, I'll take them.
Yeah, no, that makes a lot of sense. I mean, the checklist of becoming a planet is pretty simple. And one more thing, I guess, maybe that we should probably add, and that we talked about before we jumped into this recording, is that the IAU said that Pluto wasn't a primary planet because it didn't clear its neighborhood. But you and I both know if you placed Mercury or even Earth out into the Kuiper Belt, it wouldn't clear its orbit. So,
right. I mean, how important to you is it that it clears its orbit? If that's important to you, and that is important to some dynamicists, they might like that definition. But, so there's definitions, different people will use different definitions in different ways. But
That's fair.
What you care about is the processes that are at work on the surfaces and what they're made out of and how they were made.
Yeah.
You don't care if it cleared its own or not.
That's fair. Yeah, it should be more subjective to the body rather than its surroundings. I get that, definitely. So, Will, I just want to say again, thank you so much for being on the podcast and talking about Pluto science, and also taking us through way more than I knew about Pluto's determinism. And that was good. I appreciate that. So thank you.
Yeah, happy to do it. It was great to be with you, Sam.
All right, take care. We're back for the last segment, and we're going to be talking about, well, not me. Kevin's going to be talking about the dark skies legacy in Flagstaff, as well as the direction of the facility of the Lowell Observatory. So maybe we could start with the direction. I know that you have a lot of big plans there, so take it away, Kevin.
Sure. Well, when Percival founded the observatory in 1894, it was, the big thing was to do scientific research. But another part of his mentality was, he wrote about this, essentially, what's the point of doing science unless you make it available to humankind in general?
Absolutely.
And so to him, that meant, he wrote books and he invited visitors to come up to the observatory. Even I found old newspapers that within a couple months maximum, they had advertisements in the local paper saying, it's Saturday night, come on up and take a look through the telescope. And so from the beginning, he wanted to share the cosmos with people. And that really is our mission is, often we've said it's, kind of two-pronged. It's doing science research and sharing the results with the public. But I think another way of looking at it is that we talk about is it's science communication. Our scientists do research and they communicate it to fellow scientists, and we communicate it to the public. And, want to not just educate people, but inspire them. That's such a big part of what we do, is not just reporting dry details, but what's it mean? And why should we care? And besides that is, let's take a minute and gaze up at the sky and look at the wonders of the universe.
Yeah.
Let's inspire people to do that. And so that all kind of works together, this learning about space and then sharing the results and inspiring people about it. And so today we have one of the most powerful telescopes in the world, the Lowell Discovery Telescope. It's 4.3 meter in diameter, which is about 14 feet. And it's the fifth largest in the continental US. But like I said, one of the most powerful in the world, because something called a instrument cube, in which you can put a bunch of different instruments on the telescope, because the telescope collects light, but then different instruments analyze the light in different ways. And so different instruments do different things. And so you can have an imager and a spectrometer,
Right.
and there's a lot of different things you can have on there. And so it's powerful because you can nearly simultaneously use 5 instruments at the same time, which is really unusual. That's our flagship research telescope. We have others, but that's our flagship one. And And so our science is going ultra strong. What's been hot in recent times is the DART mission, sending spacecraft to asteroid and impacting it to try to divert its course as a test to see if we can do that if an actual Earth approaching asteroid would hit us. And it's been, by all accounts so far, very successful. Well, Lowell has been involved with that. A lot of observatories around the world, but Lowell's involved because before the impact, they had to do a lot of observations so we can precisely pinpoint the orbit of this thing. How do you know if it's changed if you don't know where it was in the first place?
Agreed.
So you have to pinpoint the orbit, and then after impact, doing the same kind of observations and seeing how it's moved. And so not only the Lowell Discovery Telescope, but another telescope up here we're using, the Hall Telescope. We have observers that are working on those post-impact results. And so that, that's just one example. It's a lot of times it's research that, the DART mission it got headlines around the world, and, Lowell was involved. One of the iconic pictures that came out was after impact was this debris tail that formed after the impact. And one of our little scientists was one of a 2-person team that had captured that image.
Awesome.
And so that's neat. New Horizons, when it flew by Pluto in 2015, one of the leaders of one of the teams, the surface composition team, he's Will Grundy, and he's at Lowell Observatory. So
Nice.
he's one of the leaders of that team. So it's there's a lot of not just science, but science that people are hearing about. It's exciting to be part of that. So
yeah,
we're pushing forth with every day. There's more and more discoveries being made. It's exciting. And then on the education front, right before COVID, we were getting about 105,000 visitors a year. And that was in a visitor facility designed for 60 or 70 a year. And so we are growing it. And so, what we decided our goal is to become the premier destination for astronomy education. And when I say astronomy education, that means, coming up and doing tours. You can see where Pluto was discovered and look at Percival Lowell's 100-plus-year-old telescope, but also looking through a bunch of other telescopes that can look at galaxies and planets and all sorts of things. Every night, it's like we have a star party where you can look at a lot of different things. So in the shadows of where Clyde Tombaugh discovered Pluto, our guests can make their own discoveries, as it were, of the universe. And so, and we're now building a new visitor center that will open in the summer of 2024. And it's 40,000 square feet, 3 stories, and it's a phenomenal facility. And it's going to be, a true destination here in Arizona for people around the world that want to be inspired about the cosmos. So our future it's exciting. We're growing rapidly, and part of that is not, it's because we're meeting a need. We're getting more and more visitors, and of course, on the science side, we want to be at the forefront of astronomical research. That means having the best instruments that we can get, and so cutting edge research and world class, education. And I say education, and it sounds like you're going to school, and that's good, but also it's like educational entertainment or edutainment, or I've heard different words for it, because there's nothing cooler. Well, I don't know, it depends on what you say, but looking through a telescope and gazing at something in the sky, and you're standing at the eyepiece, it's just you and what you're looking at, connecting to the universe, is a really special experience.
Mm-hmm.
And we're making it to where anybody who's capable of looking through an eyepiece can do that. They have access to it. And
that's awesome.
And so we want to make astronomy available to everybody.
Yeah. Astronomy is one of those things, categories in science where it's really easy to get somebody just curious and excited about science.
Right. Uh-huh.
Yeah, it's a good gate. It's a good gateway, I would say.
And there's space and dinosaurs. kids, you can grab their attention really fast, but adults too. There's just something special about certain things like that. And
Absolutely.
to be able to, for anybody to be able to come up here and look through a telescope, or look through the telescope that Percival Lowell used in his studies of Mars, and the telescopes that some Apollo astronauts used while they were preparing to go to the moon, or that the guy who discovered the expanding universe used it. And then all the suite of new telescopes in our Giovanni Open Deck Observatory. You roll the building back, and it's an instant star party. It's
Nice.
really phenomenal.
Nice. I'll have to come back up soon. It was nice. Whenever I was there, I was on a time budget and I couldn't stay for the night, but I need to go back up there and
Well, that's an open invitation for you to come up, and I'll get you in and make sure you see. I can't say everything because there's so much, but highlight things, and then every time you come back, you see something new.
Sounds good to me. So one of the last things we want to cover before we jump out of here is the Dark Skies Initiative in Flagstaff. Would you mind going over that?
Sure. What a heritage it is. In fact, when Percival Lowell decided to set up his observatory in Arizona, one of the driving forces was looking for dark, clear skies, because he was from Boston, the Boston area, and he talked to astronomers at Harvard about setting up an observatory, and it was clear we're in the mid 1890s. Electricity is becoming common on the East Coast. You're getting electric lights that are shining light up in the sky. You also have factories, from some factories that are owned by Lowell's family, the textile mills, and those you can't see through you can't see through smoke, and the more artificial light shining up, the less you can see the stars and planets.
Right.
And so that's the reason why he came to the American Southwest, was for dark, clear skies. And so he did that. And at the time, there's no electricity in Flagstaff, so it wasn't a problem. But the observatory is located about a mile from downtown Flagstaff.
Right.
So it's right on a mesa just west of downtown. When he set it up, it wasn't bad, but through the years, Flagstaff grew, got city lights, street lights, and we could still do observing here. But in the 1950s, the biggest telescopes we had weren't big enough anymore. The technology was advancing, telescopes were getting bigger. The bigger the telescope, the more light you can gather, the more you can see. And so we worked on acquiring a new telescope. It was called the Perkins Telescope from Ohio. And great, let's get this, but we can't really put it on the traditional location because there's now downtown Flagstaff is lit up. And so they searched for sites outside of town and found a mesa about a dozen miles southeast, but noticed that sometimes there was searchlights that would shine in the skies. And that would be, a little distracting for seeing the night sky. Well, one of our astronomers, I think he was retired by now, but still involved, because that's what so many scientists do. He had been mayor of Flagstaff at one time. His name was Earl Slifer, E.C. Slifer. And so he talked to his friends at the city, and they wrote an ordinance that kind of, defined the use of those searchlights, when you can use them, when you can't. You don't need to use them at 2 a.m., for instance, everything's closed.
Right.
That may not be the exact thing that it said, but that's the idea of, just not trying to get rid of it, but, making it logical when you use it. And so they made this ordinance. This is 1958. This is the first first outdoor lighting ordinance in the world. It was done right here. And it started because of astronomy. Well, through the years, Flagstaff and the county we're in, Coconino, modified that and made other restrictions on light, artificial light. Excuse me. So made other ordinances. And so by 2001, a group called the International Dark Sky Association, they were getting together, and really a central point for trying to preserve dark skies, because it's becoming clear that artificial light is back then we knew it was bad for astronomy, but what we've learned since then is how bad it is for wildlife. Changes the cycles and rhythms of animals and how it is on plants and such. And so people do this at different levels, but in general, the leadership of Lowell wasn't trying to just say we can't have these lights. It's finding, smarter ways of using them. You don't need to shine a light in the sky. What's the point? I mean, if you're maybe a used car lot that's trying to draw attention to that area, but really, is that necessary? And in a lot of cases, like lights at our homes that are shining upward, but you want to shine down on the sidewalk.
Right.
And so, thinking about how lights are pointed and then the type of lights, that some lighting just doesn't, it doesn't impact the darkness as much. And so in 2001, the IDA named their world's first international dark sky city, and that was Flagstaff, Arizona.
Nice.
And so that tradition continues today. Flagstaff is really kind of, I can't say the leader, but certainly a leader. And certainly so many other communities have patterned themselves after what's going on here. Just a couple of years ago, the Grand Canyon, they made some changes to the lighting and did a lot of work, and they're now a dark sky park.
Nice.
And so it doesn't lessen safety if it's done right and everything. It's just, we don't need all that excess. And I think it's, partly an example, in some ways the world we live in, a lot of, we developed, disposable packaging. Fast food restaurants made it big. And, when everybody's working to, you can go out and get something to eat, you don't have to do dishes. It made life easier, but everything comes at a price.
Of course.
And lighting, it's great to be able to, have lighting to see outside and safety and all, but there's a limit. It doesn't mean you have to have endless light. It's using it properly. And
I agree.
It's something I think there's so much more awareness now because of the impact it has, not just on astronomy, but on
Ecology.
Biology, ecology. Yeah.
Yeah.
And there's also something innate with us of connecting to the universe and being able to look up and see dark skies. And like, I've seen people come to the observatory from, like coastal areas that they looked up and said, I thought it was supposed to be clear tonight. Why are the clouds up there? And that's the center of the Milky Way galaxy. And I've seen people cry because they've never seen that. And my gosh, that's really connecting to the universe. And, we all love, well, I don't know, so many of us love, electronics, and we can do so much with them and everything, but to be able to just step outside sometimes and just turn all that off and just look up and look at our place in the universe it's part of what makes us human, that curiosity and that connection to the cosmos.
I couldn't agree more. Well, one more thing that I want to ask before we get out of here is, first of all, you are an author. So if you wouldn't mind sharing some of your book titles with me, so we can, get that out there. I'm sure they want to read more about the discovery of Pluto per se.
Sure. I've worked on 7 books, and most of them are kind of things, I call them gift shop books. They're not like biographies, or they're nonfiction, but it's because I wanted to, for like guests to Lowell Observatory and others that are interested, to be able to learn more. You come here, do a tour, that's it. We want to be able to keep the process going. So Will Grundy, our Pluto expert, and I did a book on Pluto,
Nice.
Pluto and Flagstaff. And Pluto and Lowell Observatory. And it talks about, most of the major discoveries with Pluto have some ties to Flagstaff. And so a lot of those are Lowell, but also beyond. And so that's one. We've done some Images of America books about Lowell Observatory and Northern Arizona space training. One called The Far End of the Journey. It's a coffee table book specifically about our magnificent 24-inch refracting telescope.
Nice.
I did one called Historic Tales of Flagstaff with a a friend of mine, Mike Kitt, who is a moon expert. And it's just different stories from Flagstaff history.
Cool. That's awesome. Thank you for sharing that. I figured might as well give you a plug while you're here.
Sure. Yep.
I'll make sure that I get that linked,
Okay.
and that way people can get access to your books,
Sure.
learn more about like everything that you've just said through the different books. So yeah, Kevin, I really appreciate you being on the podcast. This has been great, getting to hear more about the history, even just the sociology behind Pluto, and just covering the science, as well as learning more about the Lowell Observatory, Flagstaff, and the Dark Skies Initiative. So thank you for being on the podcast.
Well, it's great talking with you and great to share this. It's, such really great stories, and it's what makes, science and I guess life in general fun. It's the stories and the people and how, maybe it's science, but it doesn't mean it has to be, those scientists. They're people too, but there's so many great human stories. It's great to be able to talk about it.
Agreed. Well, thank you. I appreciate it, and take care.
Thank you.
That is all for this episode of Everything STEAM. I just wanted to take a quick second and thank Kevin and Dr. Grundy for taking their time to share their knowledge on Pluto. If you love astronomy and the wonders of space, I recommend you follow the Lowell Observatory anywhere you get your social media. If you ever find yourself in Flagstaff, Arizona, be sure to check out their facility and stick around for a view through their telescopes. The view of the cosmos is absolutely impeccable there. I would also love to mention my amazing team for their collective efforts to make this show happen. This podcast was edited by Ariel Piermont, marketed by Courtney Page, QC by Panyapit Eriksit, and our episode art was created by Gabrielle Edmiston. After the episode, please give our podcast a rating and review on whatever platform you get your podcasts on. We're always looking for feedback, and the rating would greatly help us out in the fight against the algorithms. Lastly, be sure to check us out on all the socials for podcast news, upcoming episodes, and fun STEAM content. Just search Everything STEAM on Instagram, TikTok, Facebook, and Reddit to join in on the fun. Once again, thank you for listening to Everything STEAM. I'm your host, Sam Stanford, and as always, stay curious.